Hi, my name is Adam. In this short video, I will explain how to write a recursive function that checks if a binary tree is a valid binary search tree, and I'll connect this to real-life examples. I'll start by giving an analogy that will help us understand what I'm trying to talk about. Think of a library bookshelf. Every book in the shelf, in the left-hand side of the shelf, must come alphabetically before the current book, and every book on the right-hand shelf must come afterwards. So, on the left-hand shelf, supposing you're looking for a book that actually starts with the letter D. All books on the left-hand shelf must be books that start from letter A to C, and then all books on the right-hand shelf will be books that start after letter D. So this same thing works for a binary section too. If a book is out of order, for example, now you see a book of letter M on the left-hand side, it automatically fails the test. So binary search tree too also work the same way. Left values must be smaller and right values must be larger. Now, how do we take this in the code? Imagine a function that starts at the root of the tree. If the node is empty, that's fine. An empty node, an empty branch is always very valid. If the node value is outside the allowed range, then the tree is not a BST. Otherwise, then we also check the left child, but we tighten the maximum bound to the current node's value because everything on the left must be smaller. We also check the right child again, but in this case, we tighten the maximum bound to the current node value. Sorry, for the right side, we tighten the minimum bound to the current node value because everything on the right must be larger. So if you are looking for minimum bound, or let's say, let me just give an analogy using a number like 2. So we must check that at the left bound of it, we use 2 as the maximum number. No number should exceed 2. Why? At the right hand side of it, we now use it as the minimum number. No number should be smaller than 2. So we also, if both sides come out as true, that means it satisfies the two conditions on both the left hand and the right hand side, then the whole tree is valid. But if either side fails, then the tree is not a BST. In real life application, these are the things we kind of use in real life system. For example, in banking software, transactions might be stored in tree for fast lookup. Making sure that the tree is valid ensures that searches are accurate and data isn't corrupted. In search engines, BST-like structures also help us to sort out results more efficiently. In summary, the recursive function checks each node against valid ranges, just like a librarian checks that books are in the right order. If one node passes, the tree is the valid BST. Thank you very much.